Hello everyone, my name is Mohammed Radwan and today I'm presenting my paper Fast Occlusion-Based Point Cloud Exploration, which is written by me, Stefan Oralinger, and Michael Wimmer from the Technical University of Vienna. We know that current scanners and sensors can capture point clouds of large scale, and while there exists levels of detailed structures that can subsample such huge sets for rendering, processing them needs some structuring of the points. The state-of-the-art data structures are built in order n log n, which is acceptable for moderate-sized datasets, but it can be prohibitive for processing sets of huge size, especially if the set is dynamically changing. Our proposal is a view-dependent structure that we name the Discrete Depth Structure, or the DDS, which is both near linear in practice and also output dominant, as I will explain later. And as an application, we introduce a framework for both rendering and exploring scenes of point clouds, where exploring is based on revealing occluded objects. Related to our work are multiple layers structures, which are constructed by projecting the data to screen space in multiple passes or in a single pass, and then finding the different depth layers of the projected data. Many structures are based on this concept and were used in applications such as controlling transparency, ray tracing, and collision detection. One such structure in particular is the TLDI, or the thickened layered depth images, which was used in collision detection, and the DDS is actually built on the same theoretical definitions of the TLDI, and both of them approximate the underlying surface of the point set. But unlike the DDS, the TLDI extracts the depth layers one by one and projects the whole dataset every time. Also related is sampling large point sets for rendering, which is done using hierarchical levels of detailed structures, which are usually multi-resolution trees. And pottery is one of these structures, and we used it in our framework for subsampling and rendering the scenes of point clouds. Also related are the different occlusion management techniques, such as viewing the scene from multiple perspectives, or virtual X-rays in which occluders are turned transparent, or volumetric probes, which the user can use to distort the scene to see the occlusions. All these methods assume the objects have a well-defined surface and are arranged in a tree-like structure such as scene graph. So, I focus now on the DDS, around which the whole approach is centered. For an input set of points, the connectivity between the points is restored using an adaptive spherical cover, where the radius of a sphere is inversely proportional to the sampling density at the corresponding point. Then the spheres can be simplified as cylinders, which are axis aligned with a projection plane. Then we discretize the projection plane into a grid of cells and also discretize the cylinders into depth intervals. And we blend the intervals of different cylinders if they intersect. So intersecting depth intervals are blended into a single depth bounding interval, or a DBI. This figure shows the blending process more clearly. A rays emanating from a cell intersects three cylinders in three fragment intervals, F1, F2, and F3. And because these three fragment intervals intersect, they are blended into one depth bounding interval, or a DBI. Blending is done by computing the start of the DBI as the weighted mean of the starts of the fragments intervals, and the same for the end of the interval. The weights are normalized Gaussian functions of the distance from the fragment interval to the point that generated it. So, how is this implemented? First, unlike the TLDI, the DDS is built in a single pass. For each point, we project a disk instead of a cylinder, and each generated fragment represents a fragment interval. The construction pipeline consists of 4 stages: count, project, sort, and blend. Now let's assume that we have these 3 points, and let's see how their fragment intervals at grid cell C are blended. For P1, for instance, the cylinder is represented by a disk. L is the length of the fragment interval, D is the depth from the projection plane to the fragment interval, or equivalently to the cylinder, and we also need to store X, which is the distance from the fragment interval to P1. And the same for the other 2 points. So at the subarrays of cell C, we have 3 fragment intervals, each one with all the information needed, and the order is random. Next, we sort the fragment intervals by depth, and then we blend the fragment intervals. In the example here, 2 depth intervals, namely the ones of P1 and P2, intersect. So they are blended in one dBi. We have 3 stages here in the figure, but in the implementation, we also have a counting stage performed before the projection stage, which determines the size of the subarrays of each cell. As for the comparison between our structure, the DDS, and other well-known structures, the construction runtime of this pipeline is of order F log L, where F is the number of fragments and L is the number of layers. And as in practical cases, L is usually a lot less than F. The algorithm is near linear in F in practice. So it is competitive with other structures such as trees and hash maps, especially if you also consider storage complexity and coalesced memory access. More details can be found in the paper. So now we use this structure in a framework for rendering and exploring point clouds. The framework has 3 main components. The rendering component is based on the levels of detailed structure, and we use the pottery in our implementation. And there are a reconstructor component builds the DDS from the subset of points selected by the pottery. And then from the DDS, an occlusion graph is built, and the explorer component uses this graph to explore the scene by hiding occluders. The list of objects to be hidden is sent from the explorer to the renderer. And for this particular application, a prerequisite is that the points are already segmented, so that each point is labeled with the ID of its object. So, why should the points be labeled? Because we should not blend fragment intervals of different objects. The DDS construction pipeline is a little modified for our specific application. We still have the count and project stages again, but now we sort the fragment intervals with respect to a compound key of object ID and depth. We blend, and then we sort again the resulting dBis based on depth. This is an example. We have 6 points. The blue points belong to one object, and the red ones belong to another. We project again. We sort the fragment intervals with respect to the compound key, so that the points of each object are consecutive. We blend the intersecting fragment intervals into dBis, and then we sort the dBis with respect to the depth. Now we have the structure. Next, we extract the occlusion relations simply by traversing the dBis along each pixel or each cell, as can be seen in this figure. And then we build an occlusion graph. The complexity of the occlusion graph depends on the number of objects, and the granularity depends on the level of segmentation. Like here in this figure, in this level, nearby objects of the same class are considered one object, like these 2 chairs. In another level, a finer one, these objects are separated. And in a third, even finer level, objects are segmented into parts. Several tools can be applied on the scene using the occlusion graph, to expose occluded objects. The first function is click an object to reveal it by hiding all its occluders. A second function is reveal by class. For instance, the user can choose to reveal all chairs by clicking one chair. In a third function, the user can see through occluders, or objects can be arranged in visibility layers. To arrange objects into visibility layers, the first layer has the objects that are not occluded at all. Then the second layer has the objects that are occluded by the first layer objects only, and so on. This arrangement of objects into layers happens automatically, and then the user can browse through these layers to understand the whole scene quickly. Now we come to the results. In our experiments, we used an indoor set. The points in this set are classified to common indoor categories like a chair or sofa or floor or a wall, etc. And in order to segment the points into objects, we use a region growing algorithm so that near points of the same category are joined in a set that represents a single object. The scene has more than 30 rooms and consists of more than 40 million points. We took 4 views from the model, and we took 4 resolutions from the first view. So first we compared the DDS with the TLDI. We used an underlying grid of size 512 by 512, and we found that the DDS is 20 to 40 times faster in construction runtime, and it is also linear in the number of fragments. Building the graph is several magnitudes faster than the TLDI, and that is because the TLDI needs to compare each pair of layers to get the occlusion relations. That makes the TLDI infeasible in the application of occlusions detection unless the scene is very small. Then we analyzed the DDS construction runtime, and we found that sorting the fragments is indeed the lengthiest stage, followed by projection. We also found that the linear stages of the pipeline sum up to almost 50% of the runtime. This further supports our claim about the linearity of the algorithm in practice. Finally, we compared the algorithm on the same view, but with 4 different resolutions. One time with 512 by 512 grid, and another time with 256 by 256 grid. And we found that the latter takes 35 to 40% less time for both DDS construction and graph building. More importantly, the construction times per resolution are very close, which means that the DDS construction runtime is output dominant. And that is because runtime is a function of the number of fragments, which is proportional to the projected surface area, which should be constant for the same view regardless of the resolution. This takes us to the conclusions. We introduced the view-dependent structure DDS, which is also a surface approximation. We proved it has an output-dominant runtime and that it is near linear in practice. And the DDS was used in a framework to render and explore scenes of point clouds, which was proved to run interactively. And these are some potential ideas for using the DDS or variations of it. The DDS can work in rendering applications as a visibility filter that discards the occluded primitives. It can also work as a data structure for points, where points are just projected and grouped in lists among cells without blending or approximating the surface at all. And it can also work as a bounding volume in applications such as simulation or deformation. And this is the end of my talk. Thank you for your attention, and if you have any questions, please ask me.